Picture a colossal jet of energy stretching across thousands of light years, spinning at impossible speeds and outshining entire galaxies. That's a pulsar jet, one of the universe's most breathtaking speed demons, accelerating particles to nearly the speed of light. Or consider hypervelocity stars, flung from the heart of our galaxy with such force that they're destined to travel alone through the intergalactic void forever. These aren't just abstract concepts or distant phenomena. They are real cosmic speedsters that defy our very understanding of physics and push the boundaries of what we once thought was possible. So what are the fastest things in the cosmos, and how do they challenge everything we know about motion, energy, and time itself? Welcome to an exploration of the universe's most astonishing velocity records, where we count down 30 incredible facts about these high-speed marvels. From the familiar, like light itself, to the utterly bizarre objects that warp space, break conventional limits, and exist in states that seem more science fiction than reality. Each discovery invites us to rethink what's possible, revealing a cosmos far stranger and more dynamic than we ever imagined. This journey isn't just about listing facts. It's about uncovering the stories behind these cosmic sprinters and understanding how their extreme speeds shape the universe around us and even influence the fate of galaxies. You're about to witness a countdown that spans the breadth of astrophysical wonder, touching on everything from runaway black holes to particles that outpace light within certain materials. Each entry is a testament to human curiosity and our relentless drive to decode the universe's deepest secrets. So settle in and open your mind to the extraordinary. Whether you're a seasoned space enthusiast or just beginning to explore the cosmos, this voyage into the fastest objects in existence promises to leave you in awe of the sheer power and elegance of the universe, and perhaps inspire you to look up at the night sky with renewed wonder. Our journey begins with the most fundamental speed limit in existence, the ultimate rule written into the very fabric of reality, the speed of light in a vacuum. This isn't just a number, it's a universal constant, precisely 299,792,458 meters per second. Think of it as the cosmos's ultimate speedometer, and no matter how powerful an object is, its needle cannot push past this value, known to physicists simply as c. This limit isn't arbitrary. It's built into the structure of spacetime itself, governing not just light but causality, the very relationship between cause and effect. It ensures that information and influence cannot travel instantaneously, preserving a logical order to the universe where the past influences the future and not the other way around. This cosmic speed limit is what makes the universe observable to us. The light from distant stars and galaxies has been traveling for millions or even billions of years to reach our telescopes, allowing us to literally look back in time. Yet, this same rule also presents profound puzzles for cosmologists. One of the most significant is called the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see that it is incredibly uniform in all directions. But if the universe has always been governed by the speed of light, there hasn't been enough time for heat or information to travel between these vastly distant regions to even out their temperature. It's as if two people standing miles apart in a foggy field, unable to see or communicate with each other, are somehow wearing identical outfits. This paradox hints that our understanding of the universe's earliest moments is incomplete, suggesting that something extraordinary, like a period of inflation, must have occurred to break this rule momentarily and set everything into equilibrium. But if the speed of light is the universe's unbreakable rule, then hypervelocity stars are the spectacular rule benders. These aren't your average, well-behaved stars orbiting placidly within the galactic disk. These are lone wolves, celestial outlaws shot out from the heart of our Milky Way at staggering velocities that can exceed 1,000 kilometers per second. To put that incomprehensible speed into perspective, at that rate, you could travel from Earth to the Moon in a mere 6 minutes. These stars are moving so fast that they have achieved escape velocity from the entire gravitational pull of our galaxy, destined to sail off into the vast, empty darkness of intergalactic space, never to return. Their incredible journey begins with a cosmic catapult, and the most likely culprit is the supermassive black hole that resides at the very center of our galaxy, Sagittarius, a star. Imagine a binary star system, two stars locked in a graceful dance around each other that ventures a little too close to this gravitational monster. The black hole's immense gravity can violently tear this partnership apart, capturing one star into a tight orbit while slingshotting its companion away at a tremendous fraction of the speed of light. It's a gravitational assist of epic, destructive proportions. This process, known as the Hill's mechanism, effectively turns the galactic core into a colossal particle accelerator for stars. The existence of these stellar speedsters forces us to completely redefine what a star's life can be. Instead of a predictable cycle within a galaxy, their story is one of sudden, violent ejection and eternal solitude. They are condemned to travel through the freezing void between galaxies, where the distances to any neighbors are so vast that their light would be the only star in an otherwise empty sky for trillions of years. Yet, even in their isolation, they serve a profound purpose for astronomers. By tracing their trajectories backward, we can map the gravitational fields of our galaxy and learn more about the mysterious environment surrounding Sagittarius, a star. They are cosmic breadcrumbs, leaving a trail that leads us directly back to the most extreme and powerful engine in our galactic neighborhood. But if a hypervelocity star is a cosmic cannonball shot across the galaxy, then a pulsar is a far more precise and relentless machine, a spinning dynamo of unimaginable power. Born from the violent death of a massive star in a supernova, a neutron star is the incredibly dense core that remains, packing more mass than our Sun into an object barely the size of a city. And when that neutron star is highly magnetized and spinning rapidly, we call it a pulsar. These objects are the universe's ultimate natural particle accelerators, capable of feats that make our most powerful human-built colliders seem like children's toys. Their secret lies in their incredible rotational energy and immensely powerful magnetic fields, which together can launch focused jets of particles and radiation from their magnetic poles at velocities incredibly close to the speed of light. This process creates the iconic lighthouse effect that makes pulsars so identifiable from Earth. The jet itself isn't constantly pointed at us. Instead, it sweeps through space like the beam of a cosmic lighthouse as the star rotates. Every time that intense beam sweeps across our line of sight, our telescopes detect a pulse of radiation which can range from radio waves to high-energy gamma rays. The rate of these pulses reveals the pulsar's spin, and some of these objects, known as millisecond pulsars, are rotating hundreds of times every single second. To grasp the physics-defying nature of that spin, consider this. The surface of such a pulsar is moving at a significant fraction of the speed of light. If you could stand on its surface, you would be hurled into space not by gravity, but by the sheer centrifugal force of its rotation. The particle jets themselves are where the real speed record is set. Charged particles like electrons and protons get caught in the pulsar's magnetic field lines near the poles and are accelerated along them to phenomenal energies. These aren't gentle streams, they are narrow, focused beams of matter and energy being ejected with such force that they can be observed across interstellar distances. The energy contained within a single pulsar jet can outshine entire galaxies, making them some of the most luminous phenomena we have ever observed. They serve as natural laboratories for studying physics under conditions we could never hope to recreate on Earth, teaching us about the behavior of matter, the nature of extreme magnetic fields, and the very limits of acceleration in our universe. Yet even the breathtaking power of a pulsar is dwarfed by the sheer scale of the engines at the hearts of galaxies themselves. To witness the universe's most powerful particle accelerators, we must look to active galactic nuclei, where supermassive black holes millions or even billions of times the mass of our Sun are actively feeding. It is here that we find relativistic jets, colossal beams of plasma that stretch for thousands of light years, and in which matter is hurtled into the void at over 99% the speed of light. The process begins with an immense disk of superheated gas and dust, known as an accretion disk, swirling around the black hole at dizzying speeds. As this material is pulled inward by the overwhelming gravity, friction and magnetic forces heat it to temperatures of millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. But not all of this doomed matter actually crosses the event horizon. Through processes we are still working to understand, a portion of this infalling material gets channeled and focused by the black hole's incredibly powerful magnetic field lines. Instead of falling in, it gets funneled away from the poles of the black hole and accelerated into two opposing narrow beams, the relativistic jets. The most famous example of this cosmic spectacle is the jet erupting from the supermassive black hole at the center of the galaxy Messier 87, an image famously captured by the Event Horizon Telescope collaboration. This jet is a mind-boggling structure extending for at least 5,000 light-years from its source. The particles within it are accelerated to such extreme velocities that they exhibit effects predicted by Einstein's theory of special relativity. From our perspective, the jet appears to be moving much faster than the speed of light, an illusion known as superluminal motion caused by the jet itself traveling almost directly toward us at nearly the speed of light. This is the universe's ultimate optical illusion, a trick of relativistic geometry that highlights just how extreme these environments truly are. The energy output of these jets is almost incomprehensible. A single active galactic nucleus can outshine every single star in its host galaxy combined. They are fundamental architects of galactic evolution, as these jets can travel far beyond their home galaxy, heating the intergalactic gas and regulating the formation of new stars across vast cosmic volumes. They are a stark reminder that black holes are not just passive destroyers but also dynamic creators, capable of shaping the cosmos on the very largest scales through the sheer, unimaginable speed of their eruptions. But for every rule, there seems to be a spectacular exception, and while relativistic jets represent matter moving at the absolute brink of light speed, there exists an even more enigmatic and far smaller class of speedster that arrives right on our cosmic doorstep. These are cosmic rays, not rays of light but a relentless, invisible rain of high-speed subatomic particles, primarily protons, that bombard our planet from every direction in space. They are the universe's smallest and most numerous bullets, traveling at velocities that make even the jets from active galactic nuclei seem almost sedate, carrying energies so immense they defy our understanding of physics itself. The journey of a single cosmic ray proton is an epic tale of acceleration across the galaxy. It begins its life, perhaps, in the chaotic aftermath of a supernova explosion, or maybe it gets caught in the immense magnetic field surrounding an active galactic nucleus. Over thousands of years, it bounces back and forth across expanding shockwaves of energy, each pass granting it a slight boost in speed, much like a surfer catching an endless series of perfect waves. This process, known as Fermi acceleration, can gradually push a single proton to an energy level that is almost incomprehensible. We're talking about particles moving at 99.9999999% of the speed of light. At that velocity, a proton would have so much kinetic energy that, from its own perspective, its journey across the 100,000 light-year width of the Milky Way would be compressed into just a few minutes due to the time dilation effects of Einstein's special relativity. When one of these ultra-high-energy particles finally collides with Earth's atmosphere, it doesn't arrive quietly. It smashes into a molecule of nitrogen or oxygen with the force of a well-hit baseball, creating a spectacular cascade of secondary particles. This resulting air shower can contain billions of electrons, positrons, muons, and photons, all spreading out over several square kilometers as they rain down toward the surface. Our detection of these events is indirect. We don't catch the original particle, but instead observe the fleeting flash of ultraviolet light this shower produces, or use vast arrays of detectors on the ground, like the Pierre Auger Observatory, to catch the secondary particles. It's a forensic investigation of a high-energy crime scene that happened dozens of kilometers overhead. The true mystery of cosmic rays lies not in how they travel, but where they come from. For over a century, since their discovery by Victor Hess in a high-altitude balloon flight, their origins have been one of astrophysics' greatest puzzles. Their paths are bent and scrambled by the magnetic fields that permeate our galaxy, making it impossible to simply look back along their trajectory to pinpoint their source. They are the ultimate anonymous messengers. While we suspect supernova remnants are responsible for many of the lower energy cosmic rays, the very highest energy ones remain a profound enigma. Their energy is so stupendously high that they shouldn't be able to be contained by the Milky Way's magnetic field, meaning the most powerful ones must come from beyond our galaxy. Yet, identifying the extragalactic engines capable of producing such particles has proven incredibly difficult. This mystery was brought into sharp focus in 1991 by a single, extraordinary event. A cosmic ray detector in Utah known as the Fly's Eye experiment recorded a particle that was so energetic it sent shockwaves through the physics community. It was immediately dubbed the "Oh my God" particle. The energy carried by this single subatomic proton was equivalent to a baseball pitch, roughly 50 joules. Think about that for a moment, the kinetic energy of a professionally thrown baseball, all packed into a single, fundamental particle smaller than an atom. It was traveling at such a breathtaking fraction of light speed that, in a race with a beam of light itself, it would only fall behind by about 50 nanometers every single second, a distance less than the width of a virus. The existence of such a particle challenges the very limits of our theories. What cataclysmic event in the distant universe could possibly serve as a cannon to fire such a projectile? To this day, no one knows for sure, making the search for the origins of these ultimate speed demons one of the most thrilling hunts in modern science. And yet, for all the incredible velocity we see in individual objects from stars to particles, the single most profound and fastest moving phenomenon in the entire cosmos involves nothing moving through space at all. We arrive at a fact that redefines our very concept of speed. The expansion of the universe itself is not just happening, it is accelerating. This isn't about galaxies rocketing away from each other like shrapnel from an explosion. Instead, the very fabric of spacetime between them is stretching, creating more space itself, and it's doing so at a rate that is constantly increasing. This means the most immense structures we know, entire galaxies, are being carried away from us by the flow of space itself, and for the most distant ones, they are receding at speeds that utterly dwarf even the fastest hypervelocity star. This astonishing discovery, one of the most important in 20th century cosmology, was completely unexpected. For decades, astronomers assumed the universe's expansion was slowing down, gradually decelerating under the steady pull of gravity from all the matter contained within the cosmos. The goal was simply to measure how much it was breaking, but in the late 1990s, two independent teams were observing distant supernova to do just that, using these exploding stars as standard candles to gauge cosmic distances. To their absolute shock, they found the opposite. The supernova were fainter than they should have been, meaning they were farther away than any model predicting a slowing expansion could account for. The only possible explanation was that the expansion of the universe wasn't slowing down, it was speeding up. This was akin to tossing a ball into the air and instead of it falling back down, watching it shoot upward faster and faster into the sky, defying gravity itself. This revelation earned the researchers the Nobel Prize in Physics in 2011 and introduced the world to the greatest mystery in modern physics, dark energy. This is where the concept of speed takes a truly bizarre turn. Because the expansion is a property of space itself, it is not bound by the universal speed limit that governs motion through space. There is no limit to how fast space can stretch. This means galaxies beyond a certain distance from us, a boundary known as the Hubble volume, are receding from Earth faster than the speed of light. Their light, emitted ages ago, is still traveling toward us through the expanding space, but any light they emit today will never reach us because the space between us is growing too quickly for the light to ever overcome the gap. They are effectively disappearing from our observable universe, fading out of existence one by one as the accelerating expansion carries them across an invisible horizon. The engine behind this great acceleration is the mysterious dark energy, a repulsive force that seems to be an inherent property of the vacuum of space itself. Think of empty space not as true nothingness, but as a seething foam of virtual particles popping in and out of existence. This quantum activity is believed to generate a negative pressure that acts against gravity, pushing the universe apart. The more the universe expands, the more space there is, and thus the more dark energy there is to cause even faster expansion. It's a self-reinforcing feedback loop of cosmic proportions, a runaway train with no brakes. The long-term implications of this accelerating expansion are both humbling and haunting. If it continues unchanged, dark energy will ultimately dictate a lonely future for the universe. Distant galaxies will vanish from view, their light forever beyond our reach. Eventually, even the nearest galaxies beyond our local group will be pulled away by the stretching space-time, leaving our galactic neighborhood isolated in an immense and ever-growing void. The universe will become a far darker, more empty place, with island galaxies scattered in an endless and ever-cooling sea of expanding darkness. This fact about the universe's accelerating growth is perhaps the ultimate expression of speed. Not the velocity of an object, but the relentless, increasing tempo at which reality itself is stretching into an unknown future. But if the accelerating expansion of space represents speed on the grandest possible scale, then our next phenomenon demonstrates a more focused, violent, and personal form of cosmic ejection. Imagine a supermassive black hole, the very anchor of a galaxy, suddenly and catastrophically evicted from its home. This isn't a slow drift, it's a gravitational coup where the universe itself delivers a kick so powerful it can send billions of solar masses screaming into the intergalactic void at up to 5,000 kilometers per second. These are runaway black holes, and their incredible speed stems from the most extreme and asymmetric events imaginable, the merger of two black holes. The story begins with a galactic collision. When two galaxies merge, their central supermassive black holes are drawn together by gravity, eventually forming a binary pair that orbits a common center of mass. As they whirl around each other, they lose energy by stirring the surrounding stars and gas, inching closer and closer over millions of years. But the final act of their dance is governed by Einstein's theory of general relativity. As the two black holes reach a critical separation, they begin to radiate their orbital energy away in the form of gravitational waves, ripples in the very fabric of spacetime itself. This emission causes their orbits to rapidly decay, culminating in a violent merger that forms a single, more massive black hole. The key to the incredible kick velocity lies in the symmetry, or rather, the lack thereof, in this final merger. If the two black holes were perfectly identical in mass and had perfectly aligned spins, the gravitational waves would be emitted symmetrically in all directions. The new black hole would simply settle into the center of the newly merged galaxy, but nature is rarely so orderly. in almost all cases there is some form of asymmetry. The black holes will have different masses, or their individual spins will be misaligned with each other and with the orbital plane. This imbalance means that during the final furious moments of the merger, gravitational waves are emitted more strongly in one direction than in others. According to Newton's third law, for every action there is an equal and opposite reaction. This principle holds true even for gravitational wave emission. As a huge pulse of gravitational radiation is shot out in one specific direction, the newly merged black hole recoils in the opposite direction, much like a gun kicking back after firing a bullet. The more asymmetric the merger, the more powerful and one-directional the final burst of gravitational waves, and the harder the recoil. In the most extreme cases, simulations show this kick can reach velocities of thousands of kilometers per second. At the top end of 5,000 kilometers per second, the black hole is moving 10 times faster than the Milky Way's escape velocity, guaranteeing it will never return. The aftermath of such an event is a scene of cosmic pandemonium. The runaway black hole, containing the mass of millions of stars, is sent careening through its host galaxy, disrupting everything in its path. But it may not leave alone. Its intense gravitational pull can wrench away an entire entourage of stars, gas, and even globular clusters, creating a brilliant, linear trail of light streaming behind it, a ghostly contrail marking its escape route. Meanwhile, back at the galactic core, the center of gravity has been violently removed. The stars that once orbited the massive central object are left bewildered, swirling in erratic orbits around a now empty center. Astronomers have actually gone hunting for these bizarre relics, searching for galaxies that appear to have a bright, active core that is visibly offset from the galaxy's kinematic center, or for those strange, linear star streams that point like an arrow toward a fleeing monster. While the gravitational kick from a black hole merger is a product of incredible forces, it is a relatively rare and tidy event compared to the next source of cosmic speed on our list, the utterly cataclysmic, universe-shaping violence of a supernova explosion. This is the spectacular death of a massive star, and in its final moments it does more than just fade away. It detonates with such ferocity that it can outshine its entire host galaxy. The outer layers of the star are not merely expelled but are blasted into the void at speeds reaching 30,000 kilometers per second, a full 10% of the speed of light. This is not a gentle drift into the night. It is a supersonic fury that forges the very elements of life and scatters them across the galaxy. The engine of this incredible expulsion is the shockwave itself. In the core of a massive star, the fusion of elements is a layered process, eventually creating an iron core. But iron is a nuclear dead end. It cannot be fused to release more energy. With its energy production halted, the core can no longer support its own immense weight against gravity, and it collapses in upon itself in less than a second. The inner part of the core crushes itself into an incredibly dense neutron star or even a black hole, while the outer core material comes crashing down at a significant fraction of light speed only to rebound off the new, impossibly hard surface of the neutron core. This rebound sends a titanic shockwave racing back out through the still infalling outer layers of the star. This shockwave is the fist that punches the star apart. It travels through the stellar material at hypersonic speeds, violently heating and compressing it. The energy transferred is so immense that it not only reverses the infall but triggers a frenzy of nuclear fusion in its wake, creating a radioactive stew of heavy elements like gold, silver, and uranium in mere seconds. The shockwave accelerates this newly forged material, hurling it outward in an expanding sphere of incandescent debris. We can see the aftermath of this incredible event in stunning nebulas like the Crab Nebula, the remnant of a supernova observed on Earth in the year 1054. The delicate, filamentary structures we see are not peaceful clouds. They are the shrapnel from that ancient explosion, still traveling outward at thousands of kilometers per second, a permanent record of that momentous detonation. The legacy of this high-speed debris is written into the cosmos and into us. This ejected material, rich with heavy elements, slams into the surrounding interstellar medium, sweeping it up and enriching it with the chemical building blocks for rocky planets and ultimately life. Every atom of oxygen we breathe, every particle of iron in our blood, and every speck of calcium in our bones was once forged in the heart of a massive star and then catapulted across space by one of these unimaginably powerful explosions. The supernova's incredible speed is not just a spectacle, it is the primary delivery mechanism that distributes these essential elements, ensuring that the death of one star can become the birth of future worlds and perhaps living beings. While the explosive death of a star can fling its own material across the galaxy at incredible speeds, the gravitational chaos within a star system can achieve a different and perhaps even more lonely form of ejection. We now turn from stellar shrapnel to entire worlds cast adrift, to the rogue planets hurtling through the interstellar void at hundreds of kilometers per second. These are not merely planets on distant orbits, they are true orphans of the cosmos, completely unbound from any star, condemned to an eternal night. The genesis of these hypervelocity planets is a story of gravitational betrayal. Most are believed to be born in the conventional way, forming from the protoplanetary disk of dust and gas that swirls around a young star. But in a young star system, the planetary billiards table is a crowded and unstable place. Gravitational interactions between massive planets like Jupiter-sized giants can be incredibly dramatic. If two such planets have a close encounter, one can be slingshotted inward, while the other is flung outward with such tremendous force that it achieves escape velocity from the entire system. This gravitational slingshot effect transfers orbital energy from one planet to the other, effectively using the star's gravity as a catapult to launch a world into the abyss. In some cases, if a star system passes too close to another star, the interloper's gravity can disrupt the delicate orbital dance and pluck a planet right out of its home, sending it careening into interstellar space. Once ejected, the journey of a rogue planet is one of profound isolation. Devoid of a host star, it plunges through the freezing vacuum of interstellar space, where temperatures hover just a few degrees above absolute zero. Its surface, if it ever had oceans or atmospheres, would quickly freeze into a permanent global ice age. The sky above would offer no sunrise, no sunset, only an unwavering, star-studded blackness, a view that would change imperceptibly over millions of years as the planet travels on its solitary path. Any potential for life as we know it would be snuffed out, buried under kilometers of ice with no external source of warmth or energy. Yet, the existence of these frozen nomads forces us to reconsider the very definition of a planet and where life might possibly exist. Current estimates suggest there could be billions, even trillions of these rogue worlds wandering our galaxy alone, vastly outnumbering the stars. This raises a fascinating astrobiological possibility. While a rogue planet's surface would be frozen solid, a massive one with a thick hydrogen atmosphere could trap enough internal heat from radioactive decay in its core to maintain a vast subsurface ocean of liquid water. In such a dark subsurface sea sealed off from the universe above, life might not only persist but thrive, entirely independent of any star, powered by geothermal vents on the ocean floor. It's a haunting thought that the most common abode for life in the galaxy might not be on an Earth-like world orbiting a sun, but in the lightless, deep oceans of a planet drifting alone between the stars. But if the sheer velocity of these cosmic objects stretches our imagination, the underlying physics warps reality itself. As we approach the universe's ultimate speed limit, the laws governing our everyday experience begin to break down, replaced by the bizarre and counterintuitive rules of Einstein's special relativity. This isn't just a theoretical curiosity. For the particles and objects we've been discussing, these effects are a constant and dramatic part of their existence. The faster an object moves through space, the more significantly its perception of time, length, and even mass deviates from our own stationary viewpoint. It's a fundamental reshaping of reality that occurs at these extreme velocities. Consider one of those ultra-high-energy cosmic ray protons we talked about earlier, screaming through the void at 99.9999999% of the speed of light. From our perspective here on Earth, its journey from a distant supernova remnant across the 100,000 light-year breadth of the Milky Way would take it at least 100,000 years. But from the proton's own point of view, something utterly miraculous happens. Due to an effect called time dilation, its internal clock slows to a near standstill relative to ours. The entire galactic crossing, a trek that spans the lifetime of humanity, is compressed from the proton's perspective into a matter of mere minutes or even seconds. It effectively time travels into the future, arriving at Earth having experienced almost no passage of time at all since its acceleration. This same principle works in reverse for distance. A phenomenon known as length contraction means that for our speedy proton, the universe itself appears squashed in the direction of its travel, those 100,000 light-years of mostly empty space. From its relativistic viewpoint, that vast distance is contracted down to a relatively short trip. It's as if the entire galaxy has been squeezed into a smaller, thinner package, making its destination much closer and more easily reachable. This isn't an illusion. In the proton's reference frame, the distance genuinely is shorter. These twin effects, time dilation and length contraction, are two sides of the same coin, ensuring that the speed of light remains constant for all observers, a foundational pillar of modern physics. The third mind-bending consequence is the increase in mass. As an object's velocity increases, so does its relativistic mass, requiring ever more energy to continue accelerating it. At 10% of light speed, this effect is negligible, but as you push closer and closer to the ultimate limit, the mass begins to balloon toward infinity. To actually reach the speed of light would require an infinite amount of energy, which is why it's a universal speed limit that nothing with mass can ever breach. This is the ultimate cosmic brake pedal. For a particle in a pulsar's jet or an active galactic nucleus, its effective mass is vastly greater than it would be at rest, which in turn affects how it interacts with magnetic fields and other particles it encounters on its journey. These relativistic effects are not just abstract equations, they have real, observable consequences that astronomers must account for. When we look at the jets erupting from active galactic nuclei, the material moving toward us at nearly the speed of light appears brighter and more energetic due to a phenomenon called relativistic beaming. Its light is focused into a narrow cone and boosted to higher frequencies, making that side of the jet disproportionately luminous. Meanwhile, the jet moving away from us appears incredibly faint and redshifted, almost as if it's not there at all. This is why we often see these jets as one-sided. Relativity itself is hiding the receding side from our view. This bizarre behavior of light and motion is a direct validation of Einstein's century-old theories playing out on a galactic scale. Yet for all the immense power of supernova and the lonely journeys of rogue planets, some of the universe's most astonishing speed records are set by events so fleeting we almost missed them entirely. These are fast radio bursts, or FRB, and they represent one of the most enigmatic and energetic puzzles in modern astronomy. An FRB is a spectacular burst of radio waves that typically lasts for just a few thousandths of a second, a blink of an eye so brief that for decades they slip through our nets of observation. But within that millisecond, an FRB can release more energy than our sun puts out over 80 years. It's the ultimate cosmic flash in the pan, a scream of energy across the radio spectrum that travels for billions of years at the speed of light to finally be captured by our telescopes for less time than it takes you to blink. The story of their discovery reads like a classic tale of scientific serendipity. In 2007, a young astronomer named David Narkevic was sifting through old archival data from the Parkes Radio Telescope in Australia, looking for entirely different phenomena called pulsars. As he scanned the records, he found a signal so powerful and so bizarre that it was initially dismissed as terrestrial interference, perhaps a glitch from a microwave oven in the observatory's break room. But this signal was different. It was dispersed, meaning the higher frequencies arrived at the telescope a fraction of a second before the lower frequencies. This dispersion is a telltale sign that a signal has traveled through vast clouds of ionized gas in intergalactic space, and the amount of dispersion revealed this particular burst had come from an almost unimaginable distance. It wasn't from a nearby oven, it was a message from billions of light years away, a single, incredible spike of energy that had been traveling through the void since before Earth even existed. Pinpointing the source of these incredibly fast events has been a monumental challenge, precisely because they are so brief and unpredictable. Modern telescopes like the Canadian CHIME instrument have revolutionized the hunt, acting as a cosmic surveillance system that constantly monitors huge swaths of the sky. Their efforts have paid off, allowing astronomers to trace many FRBs back to their host galaxies. The leading suspect for at least some of these bursts is a type of neutron star we've already met but pushed to its absolute limit, the magnetar. Imagine a neutron star with a magnetic field 1,000 trillion times more powerful than Earth's. These fields are so strong they could wipe a credit card clean from halfway to the moon. The crust of a magnetar is under unimaginable strain, and occasionally it can snap in a starquake, a seismic event that releases a cataclysmic amount of energy, potentially powering an FRB. In April 2020, a magnetar within our own galaxy, known as SGR 1935 plus 2154, was observed producing an FRB-like burst, providing the first direct evidence linking these extreme objects to the mysterious signals. But the mystery is far from solved. While some FRBs are one-off events, others are repeaters, firing off multiple bursts from the same location over days or years. This repeating behavior is harder to explain with a one-time cataclysm like a starquake or a merger. It suggests a source that can generate these immense energies repeatedly, perhaps through some kind of powerful, recurring engine. Theories abound, ranging from highly magnetized neutron stars interacting with surrounding debris to more exotic possibilities like cosmic strings or even, in the most speculative realms, advanced extraterrestrial technologies. Regardless of their ultimate cause, FRBs are more than just a curiosity, they are powerful tools. As these radio waves travel across the universe, they pass through the diffuse gas between galaxies. The dispersion of the signal allows scientists to measure the total amount of material the burst has passed through, effectively weighing the missing ordinary matter in the universe that has long eluded our other methods of detection. They are the ultimate cosmic messengers, using their incredible speed and brevity to carry a faint imprint of everything they have passed through on their billion-year journey to our telescopes. Yet for all the cosmic fireworks we've explored, from hypervelocity stars to relativistic jets, some of the most profound speed records are held not by natural phenomena, but by objects we built with our own hands. These are the Pioneer and Voyager probes, humanity's fastest and most distant artifacts, sailing silently through the void. While their velocities, Voyager 1 moves at about 17 kilometers per second relative to the Sun, may seem almost pedestrian compared to the near-light speed marvels we've discussed. They represent a monumental achievement of human ingenuity and a poignant testament to our desire to reach beyond our own world. Their incredible speed wasn't achieved by raw rocket power alone, but through a masterful application of celestial mechanics known as a gravity assist. Think of it as a cosmic slingshot, As a spacecraft flies close to a massive planet like Jupiter, it falls deep into the planet's gravitational well, gaining a tremendous amount of kinetic energy. As it swings around and escapes, it steals a tiny bit of the planet's own orbital momentum. From the perspective of the Sun, the spacecraft is flung away at a much higher velocity than it arrived with. The Voyager missions executed this ballet to perfection. Voyager 1 used close flybys of both Jupiter and Saturn to gain enough speed to break free of the Sun's gravitational pull entirely, setting it on its current path into interstellar space. It was a carefully calculated gravitational theft that turned our robotic envoys into the fastest human-made objects in history. The journeys of these probes redefined patience and perspective. Voyager 1, launched in 1977, took over 35 years just to reach the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium. It is now so distant that a signal from Earth traveling at the speed of light takes over 22 hours to reach it and another 22 hours for its reply to come back. Each day, it recedes from us by another 1,470,000 kilometers, carrying with it a golden record containing sounds and images of Earth, a message in a bottle cast into the ocean of the galaxy. Their ultimate fate is one of profound and beautiful loneliness. These silent travelers will not encounter another star system for tens of thousands of years. They will drift through the vast, empty stretches between the stars, their instruments long dead, their power sources depleted. They are our legacy, destined to outlast not only everyone alive today, but likely human civilization itself, carrying a snapshot of our world into a future we cannot imagine. They are a reminder that while our speeds may be slow on the cosmic scale, our ambition to explore and our drive to send something of ourselves into the unknown is one of the most powerful forces in the human experience. Yet even the fleeting, phenomenal energy of a fast radio burst is dwarfed by a far more cataclysmic and luminous event, one that stands as the single most powerful explosion the universe can produce since the Big Bang itself. We now arrive at the phenomenon of gamma-ray bursts, or GRBS. If a supernova is a stellar cannon, a gamma-ray burst is the cosmic equivalent of a nuclear warhead detonating with the focused power of 1 billion trillion suns, all channeled into two narrow, relativistic jets of pure energy. For those few seconds, it can outshine every star in every galaxy in the observable universe combined. And the secret to its unimaginable power lies in the breathtaking speed of its jets, which race outward at 99.9999% the speed of light. These events are so immensely powerful that they are categorized into two distinct types, each with its own terrifyingly violent origin story. Long-duration gamma-ray bursts, which can last from 2 seconds to several minutes, are thought to be the birth cries of stellar mass black holes. They occur when a very massive, rapidly spinning star, a Wolf-Rayet star, exhausts its nuclear fuel and collapses. But this isn't a standard supernova, it's a hypernova. In this extreme scenario, the collapsing core doesn't just form a neutron star, it immediately creates a black hole. The infalling material from the outer layers of the star forms a thick, swirling accretion disk around this newborn singularity. And along the star's rotational axis, where resistance is lowest, the incredible physics of the event takes over. Intense magnetic fields and neutrino annihilation funnel the titanic energy of the collapse into two opposing jets that blast their way out through the star, drilling their way through the stellar body like cosmic blowtorches. The shorter bursts, lasting less than 2 seconds, are believed to originate from an even more extreme and dense merger, the collision of two neutron stars, or a neutron star and a black hole. As these incredibly massive objects spiral inward, they rip each other apart with immense tidal forces, flinging out a spray of neutron-rich material. In the final milliseconds before they merge into a single black hole, a similar process unfolds. A portion of the debris is accelerated into ultra-relativistic jets, and it is the interaction within and around these jets that generates the initial pulse of gamma rays. In 2017, the detection of gravitational waves from a neutron star merger, followed immediately by a short gamma ray burst, confirmed this hypothesis in a watershed moment for multi-messenger astronomy, linking the warping of spacetime itself to the most brilliant flash of light we can observe. The speed of these jets is not a minor detail. It is the absolute key to understanding their incredible luminosity and the bizarre afterglow they produce. Because the material in the jet is moving at such an extreme fraction of light speed, the effects of special relativity dominate everything we observe. The light and radiation produced within the jet is beamed into a very narrow cone along its direction of motion, a consequence of relativistic aberration. From our perspective, if we are fortunate enough to be looking directly down the barrel of this cosmic gun, the entire energy of the explosion is focused and amplified directly at us. This explains how something so distant can appear so impossibly bright. We are seeing a highly concentrated beam of energy, not a spherical explosion. If we were viewing the same event from the side, it would appear thousands of times fainter, and we might not recognize it as a gamma ray burst at all. This incredible velocity also creates a spectacular and long-lasting aftermath known as the afterglow. As the ultra-relativistic jet plows into the tenuous gas of the interstellar medium, it creates a massive shock wave. The particles caught in this shock are accelerated to near light speeds themselves and begin to radiate across the electromagnetic spectrum, from X-rays down to radio waves. This afterglow can be observed for weeks or even months after the initial gamma ray flash has faded, allowing astronomers to pinpoint the burst's host galaxy and measure its colossal distance. The study of these afterglows has been crucial, revealing that many long bursts occur in distant, faint galaxies that are actively forming stars, precisely the environments where massive, short-lived stars are born and die. These are not local events. They are flashes from the far reaches of the universe, carrying information from when the cosmos was young, making them not just incredible explosions but also vital probes for understanding the history and structure of the universe itself. But if gamma-ray bursts represent the ultimate flash of light from a cataclysm, there is another, far more subtle messenger that travels at the exact same speed, carrying a story written not in photons, but in the very warping of the cosmos. This brings us to a profound confirmation about the nature of reality itself. Gravitational waves, the ripples in the fabric of space-time, travel at precisely the speed of light. This fact, confirmed by humanity's first detection of these waves in 2015, connects the unimaginable speed of colliding black holes directly to the fundamental constant that governs our universe. For a century, Einstein's theory of general relativity predicted that accelerating masses should produce these ripples, much like a moving boat creates waves on the surface of a pond. But these aren't waves in water or air. They are literal distortions in the four-dimensional continuum of spacetime itself, stretches and squeezes that propagate outward from their source. And according to the theory, they had to travel at speed c, the same universal speed limit as light. This wasn't just a minor detail, it was a cornerstone of the theory's mathematical foundation, linking gravity directly to the geometry of the universe. Yet for decades, this remained a theoretical prediction. The waves were so infinitesimally small that Einstein himself doubted we would ever have instruments sensitive enough to detect them. That all changed on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, recorded a signal that would revolutionize astronomy. For just 0.2 of a second, the laser beams in the 4 long arms of the observatory were perturbed by a passing wave that stretched one arm and squeezed the other by a distance 1,000 times smaller than the nucleus of an atom. The signal was a perfect chirp, rising in frequency and amplitude, and it matched exactly what supercomputer simulations predicted for the final moments of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging over 1.3 billion light-years away. The detection was a triumph of human ingenuity, but it was also a direct test of Einstein's prediction. By measuring the arrival time of the signal at the two widely separated detectors, scientists could confirm that the waves had traveled at the speed of light with a precision that would have astonished even Einstein. This confirmation is more than just a checkmark for a 100-year-old theory. It fundamentally links the fastest objects we've discussed to the waves they produce. The merging black holes that create these waves are themselves moving at a significant fraction of light speed in their final, furious orbits. The gravitational waves they generate carry away orbital energy at the speed of light, causing the black holes to spiral inward even faster in a runaway process that culminates in a collision of unbelievable power. The event detected by LIGO converted roughly 3 solar masses of pure energy into gravitational waves in a fraction of a second, briefly outshining every star in the observable universe combined in its gravitational output. The waves themselves are the product of this ultimate acceleration, and they travel outward at the universe's maximum allowed speed, carrying a pristine record of the violent event that created them. This discovery opened an entirely new window on the cosmos, one that is not dependent on light. We can now hear the universe through these vibrations in space-time, allowing us to perceive events that are completely dark to traditional telescopes, like the collision of two black holes in the void. The fact that these waves travel at light speed is crucial for this new field of multi-messenger astronomy. When a gravitational wave signal is detected, astronomers can immediately point their telescopes to the region of sky it came from, knowing that any associated flash of light or other electromagnetic radiation will have arrived at Earth at virtually the exact same moment. This is how, in 2017, the merger of two neutron stars was observed in both gravitational waves and light, leading to the confirmation that such events forge heavy elements like gold and platinum. The speed of these waves is not an abstract concept. It is the synchronizing clock that allows us to piece together the full story of the most extreme events in the universe, connecting the ripple in space-time to the flash of light that follows. But while the titanic explosions of distant gamma-ray bursts and the subtle ripples of gravitational waves captivate our imagination, we needn't look billions of light-years away to witness the raw, terrifying power of relativistic speed. Our very own Sun, the steady, life-giving star at the center of our solar system, is capable of unleashing some of the most violent and high-speed eruptions in our cosmic neighborhood. During a coronal mass ejection, the Sun can violently expel billions of tons of superheated plasma, a cloud of charged particles and magnetic fields directly into space at velocities that can approach 3,000 kilometers per second. To put that into a human scale, that's enough energy and matter to cover the distance from the Earth to the Moon in a little over 2 minutes, a journey that takes our spacecraft days. The engine behind this incredible acceleration is a process known as magnetic reconnection, a fundamental force of nature that operates like a cosmic slingshot. The Sun's surface is a turbulent sea of magnetism, with powerful magnetic field lines constantly twisting, stretching, and tangling like overwound rubber bands. These field lines are generated by the churning, electrically conductive plasma deep within the Sun. As they become increasingly strained, they can suddenly snap and rearrange themselves into a new, more stable configuration. This sudden snapping is magnetic reconnection, and it releases a catastrophic amount of stored magnetic energy in an instant. It's akin to the energy released when a twisted rubber band finally breaks, but on a scale so immense it can power a stellar eruption. This released energy does two things simultaneously. It heats the local solar material to tens of millions of degrees, creating the brilliant flash of a solar flare, and it acts as a powerful accelerator, catapulting a vast portion of the Sun's outer atmosphere, the corona, away from the star's gravitational pull as a coronal mass ejection. When one of these immense clouds of magnetized plasma is aimed directly at Earth, the consequences connect these abstract cosmic speeds directly to our daily lives. Traveling at such a high velocity, a coronal mass ejection can cross the 93 million-mile gap between the Sun and Earth in as little as 18 hours. When it arrives, it doesn't arrive quietly. The cloud slams into Earth's protective magnetic bubble, our magnetosphere, causing it to shake and vibrate violently. This disturbance induces powerful electrical currents in the ground and in our long-distance power lines, potentially overloading transformers and causing widespread blackouts that could last for weeks or even months. The most famous example of this was the Carrington event of 1859, a solar storm so powerful that it caused telegraph systems across Europe and North America to fail, with operators receiving shocks and telegraph paper catching fire from the induced currents. Auroras, normally confined to the polar regions, were seen as far south as the Caribbean. In our modern, technologically dependent world, the impact of a similar event today would be catastrophic on a global scale. Beyond the power grid, a major coronal mass ejection would wreak havoc on satellites, frying their sensitive electronics and disrupting everything from GPS navigation and global communications to weather forecasting and financial transaction systems. It would be a stark reminder that the speeds achieved by cosmic objects are not just distant curiosities for astronomers. They are a very real part of our physical environment with the power to fundamentally alter the course of human civilization. This ongoing dance between the Sun's ferocious power and our fragile technology underscores why scientists now monitor our star so closely, using a fleet of spacecraft to provide early warning of these high-speed solar storms, giving us a precious few hours to hopefully safeguard our vital systems against the Sun's incredible and incredibly fast fury. But even as we marvel at the explosive power of our own Sun, it's easy to forget that we are not passive observers of this cosmic motion. We are active participants hurtling through the galaxy at breathtaking speeds ourselves. Our entire solar system is on a grand, sweeping journey around the center of the Milky Way, traveling at approximately 230 kilometers per second. To put that into a more familiar context, that's about 515,000 miles per hour. At this incredible velocity, we are covering the distance from the Earth to the Moon in well under an hour, a trip that takes our fastest spacecraft days to complete. This isn't a theoretical speed, it is our constant, actual velocity through the galactic void, a motion so smooth and constant we cannot feel it, yet it defines our place in the cosmos. This orbital dance is governed by the immense gravitational pull of the galactic center, which holds our Sun and hundreds of billions of other stars in a vast, swirling disk. Our solar system is located roughly 27,000 light-years from this center, out in one of the galaxy's spiral arms. From this vantage point, it takes us approximately 230 million years to complete a single full orbit, a period of time known as a cosmic year. The last time our planet was in this same position in the galaxy, the dinosaurs were just beginning their rise to dominance during the Triassic period. In the entire history of complex life on Earth, our planet has completed fewer than 20 trips around the Milky Way. This timescale is a humbling reminder that human history, and even the entire saga of life on our planet, is just a brief moment in the context of our galaxy's rhythm. Yet, this orbital motion is just one component of our journey. The Milky Way itself is not stationary. It is a moving island in the expanding sea of the universe. Our entire galaxy, with all its stars, gas, dust, and our solar system along for the ride, is moving through space at an even more staggering velocity relative to the remnant radiation from the Big Bang, the cosmic microwave background. This universal reference frame reveals our true motion through the cosmos. Measurements show the Milky Way is traveling at about 600 kilometers per second, or nearly 1.3 million miles per hour, in the general direction of the constellation Centaurus. This movement is largely due to the gravitational pull of other massive structures in our local universe, particularly the Great Attractor, a mysterious concentration of mass millions of light years away that is drawing our local group of galaxies toward it. This multi-layered motion means we are simultaneously spinning on Earth's axis, orbiting the Sun, circling the galactic core, and being carried along by the galaxy itself through the intergalactic medium. It's a cosmic nesting doll of velocities, each one faster and on a grander scale than the last. While we feel utterly stationary in our daily lives, the reality is we are on a perpetual, high-speed voyage through the universe, a journey that has been ongoing for billions of years and will continue for billions more, a silent, majestic cruise through the starry night. But for every rule, there is a spectacular exception, and while the speed of light is a universal constant for anything with mass, there exists an entire class of particles that are born racing at this ultimate velocity, only slowing by the tiniest fraction because they possess the most ghostly hint of mass imaginable. These are neutrinos, the universe's ultimate subatomic speedsters, so ethereal and non-interactive that trillions of them are passing through your body every single second without you ever noticing. They are the closest thing to pure energy embodied as a particle, and their existence challenges our very definition of what it means to have mass and to move. The story of a neutrino begins in the heart of a nuclear reaction, and our own Sun is a prolific neutrino factory, deep within its core, where temperatures and pressures are immense enough to fuse hydrogen into helium. For every 4 protons that become a helium nucleus, 2 of them are converted into neutrons. This process isn't clean. It requires the transformation of 2 protons via the weak nuclear force, and each of those transformations releases a neutrino. This means the Sun's core is a constant storm of these particles, with an estimated 195 billion neutrinos streaming from every square centimeter of its surface every second. And because they barely interact with matter, they escape the Sun immediately, unlike photons of light which can take tens of thousands of years to bounce their way to the surface. The neutrinos generated in the core today are arriving at Earth just over 8 minutes later, offering us a real-time glimpse into the heart of our star. Their journey from the Sun to us is a demonstration of their incredible speed and ghostly nature. Traveling at 99.9999999% of the speed of light, a solar neutrino covers the 93 million miles to Earth in approximately 8 minutes and 20 seconds, a time almost identical to that of a photon. But upon arrival, their behavior is utterly different. While light is absorbed, reflected, or scattered by our atmosphere, a neutrino behaves as if our planet doesn't even exist. It can pass through all 7,900 miles of Earth's solid iron core as if it were empty space, its path completely uninterrupted. This is because neutrinos only interact via the weak nuclear force and gravity, and their cross-section for interaction. The probability they will hit anything is astonishingly small. It would take a block of lead roughly 1 light-year thick to have a 50% chance of stopping a single neutrino. They are the universe's ultimate phantoms, everywhere and yet almost entirely undetectable. This elusive quality made their discovery one of the great detective stories of physics. They were first proposed in 1930 by Wolfgang Pauli as a desperate remedy to explain a seeming violation of energy conservation in a type of radioactive decay called beta decay. Pauli was so convinced his proposed particle would never be found that he famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." It took another 26 years before Clyde Cowan and Frederick Riones finally did detect them, using the immense flux of neutrinos produced by a nuclear reactor. Their experiment, placed near the Savannah River site, was a masterpiece of ingenuity, designed to catch the extremely rare instance when a neutrino would actually interact with a proton to create a neutron and a positron, producing a unique double flash of light in a large tank of water. Their success earned Rienzi a share of the Nobel Prize and opened an entirely new window onto the universe. Yet the Sun is just one source in a cosmic sea of these particles. The most colossal neutrino generators are the cataclysmic deaths of massive stars. When a star goes supernova, an estimated 99% of the total energy of the explosion is not carried away by light or kinetic energy but by neutrinos. In the few seconds of a core collapse supernova, more neutrinos are produced than there are stars in the observable universe. This was spectacularly confirmed in 1987 when detectors on Earth picked up a burst of 24 neutrinos from supernova 1987A, which occurred in the Large Magellanic Cloud. These neutrinos arrived hours before the visible light from the explosion, simply because they could escape the dying star immediately while the shockwave took time to reach the surface. That tiny handful of detections from an event 168,000 light-years away marked the birth of neutrino astronomy, proving these ghosts could be used as messengers from the most violent events in the cosmos. For decades, the prevailing theory held that neutrinos were truly massless like photons and thus had to travel at exactly the speed of light. But nature, as it often does, had a surprise in store. Experiments began to hint at a phenomenon called neutrino oscillation, where one type or flavor of neutrino electron, muon or tau, could spontaneously transform into another as it traveled. This bizarre quantum metamorphosis can only happen if neutrinos have mass, however infinitesimal. This discovery was so profound that it earned the 2015 Nobel Prize in Physics. We now know that neutrinos do have mass, but it is so vanishingly small that we cannot yet measure it directly, only observe its consequences. The current upper limit suggests the heaviest neutrino is at least 500,000 times lighter than an electron. This tiny mass has a fascinating, almost philosophical implication for their speed. Because they have mass, they cannot quite reach the speed of light. They must travel just a hair slower, but the difference is so minuscule as to be almost meaningless on any human scale. Over a journey of 1 billion light-years, the very fastest neutrinos would lag behind a true photon by barely a few seconds. They are the universe's ultimate silver medalists, losing the race by such an imperceptibly small margin that for all practical purposes, they are still the fastest massive particles in existence. Their incredible velocity and ghostly nature make them not only fundamental to our understanding of particle physics, but also invaluable tools for probing environments we could never otherwise see, from the burning core of our sun to the chaotic maelstrom of a collapsing star. While the gravitational waves from merging black holes ripple through space-time and solar neutrinos ghost through our planet, the most luminous persistent objects in the universe are orchestrating a different kind of high-speed phenomenon, one that can shape the destiny of entire galaxies. These are the quasars, and at their hearts, they are not just brilliant beacons but powerful engines capable of driving colossal winds of gas outward at a staggering 20% the speed of light. This isn't a gentle solar breeze. It's a hurricane of superheated plasma screaming into the void with enough force to dictate whether a galaxy will birth new stars or fade into a dormant state. To understand the sheer power behind these quasar outflows, we must first appreciate the engine itself. A quasar is the intensely bright core of a distant active galaxy, and its brilliance comes from a supermassive black hole that is actively feasting. Imagine a black hole millions or even billions of times the mass of our sun, surrounded by a vast, swirling disk of gas and dust, an accretion disk that glows white-hot from the immense friction and gravitational forces at play. As material spirals inward toward the event horizon, it releases a phenomenal amount of energy across the entire electromagnetic spectrum, outshining every star in its host galaxy combined. But not all of this infalling matter is doomed to vanish. A fraction of it gets caught up in the black hole's incredibly powerful magnetic fields or is heated by the intense radiation until it is blown outward, not in a focused jet but in a more spherical, high-velocity wind. The speed of this wind is what truly defies comprehension. We are talking about clouds of gas, often heavier elements like iron and oxygen, being accelerated to 60,000 kilometers per second. At that velocity, you could travel from Earth to the Sun and back again in just over 13 seconds. This wind isn't just fast, it's also immense in scale, often billowing out to cover regions of space larger than our entire solar system and carrying enough mass to forge millions of stars. The mechanism behind this acceleration is a complex interplay of forces. The incredible radiation pressure from the blazing accretion disk literally pushes on the gas, while magnetic fields help to channel and sling it away from the central black hole. It's a cosmic tug of war where the outward forces of radiation and magnetism temporarily overpower the immense inward pull of gravity. This process is far more than just a spectacular display of power. It represents one of the most critical feedback mechanisms in the evolution of galaxies, a concept known as quasar feedback. For a long time, cosmologists had a puzzle. The largest galaxies in the universe seem to have old, red populations of stars and very little active star formation. Theories suggested that the energy output from their central supermassive black holes must somehow be responsible for shutting down star birth, and quasar outflows are the smoking gun. As these high-speed winds blast through the host galaxy, they do two things. First, they violently heat the vast reservoirs of cold, dense gas, the very raw material needed to form new stars, preventing it from cooling and collapsing. Second, they can physically push that gas right out of the galaxy entirely, ejecting it into the intergalactic medium in a process called galactic quenching. The effect is profound. A quasar can essentially starve its own galaxy to death, cutting off the fuel supply for future generations of stars and condemning it to a quiet, aging existence. This feedback loop is a beautiful and violent example of self-regulation. The same black hole that grew by consuming gas ultimately uses its own energy to prevent further growth, both for itself and for the galaxy it resides in. This explains why we don't see endlessly growing galaxies and why the masses of central black holes are so closely correlated with the properties of their host galaxies' central bulges. They are entwined in a gravitational and energetic dance, with these incredibly fast outflows acting as the decisive step that brings the music to a close, leaving a massive but silent, elliptical galaxy in its wake. But while quasars blast winds across the universe and our solar system cruises around the galactic core, there are massive structures much closer to home hurtling through space at velocities that defy the Milky Way's graceful rotation. These are high-velocity clouds, immense archipelagos of predominantly neutral hydrogen gas, some larger than constellations, traveling on trajectories that make them cosmic outsiders in our own galactic neighborhood. Unlike the orderly, rotating disk of the galaxy, these clouds are moving at speeds up to several hundred kilometers per second, often on radial paths that suggest they are either falling into the Milky Way for the first time or are being violently ejected from it. The discovery of these ghostly giants was a byproduct of the dawn of radio astronomy. As scientists began tuning into the universe at radio wavelengths, they found a pervasive whisper at the 21-centimeter line, the specific frequency emitted by neutral hydrogen atoms as their electrons change spin states. By mapping this signal, they could trace the distribution and motion of vast, cold clouds of gas that are completely invisible to optical telescopes. To their surprise, a significant portion of this gas was not moving with the predictable rotational curve of the galaxy. It was streaking through the halo on entirely independent, high-speed orbits. This revealed an entire ecosystem of fast-moving gas that had been hidden in plain sight, a dynamic and chaotic component of our galaxy's structure. The origins of these high-velocity clouds are as diverse as their sizes and speeds, painting a picture of a galaxy that is constantly interacting with its environment. Some of the largest complexes, like the Smith Cloud, are believed to be intergalactic immigrants. This enormous stream of gas, containing enough material to form 2 million suns, is on a return journey after being ripped from the Milky Way's disk by a close encounter with a dwarf galaxy billions of years ago. It is now plummeting back toward the galactic plane at over 300 kilometers per second, and when it collides in about 30 million years, it will ignite a spectacular firestorm of new star formation, seeding the spiral arm with fresh fuel for future solar systems. Other clouds are the product of a brilliant recycling process known as the galactic fountain. Massive stars and supernova within the galaxy's disk don't just explode quietly. Their ferocious energy can blow enormous bubbles of hot gas straight up out of the plane of the galaxy, lofting material hundreds of thousands of light years into the halo. There, in the cold of intergalactic space, this hot gas cools and condenses into dense clouds of neutral hydrogen. These clouds, now much heavier and colder, then succumb to the Milky Way's gravity and come raining back down onto the disk like a celestial waterfall. This constant cycle of ejection and accretion is a vital mechanism for regulating star formation, distributing heavy elements forged in supernova across the galaxy, and ensuring the galactic disk doesn't exhaust its fuel supply too quickly. Yet another class of these clouds tells a tale of galactic cannibalism. As the Milky Way's immense gravity tears apart smaller satellite galaxies like the Large and Small Magellanic Clouds, it doesn't just strip away stars, it pulls vast streams of gas away in long, filamentary structures that stretch across the sky. These tidal tails, such as the Magellanic Stream, are essentially rivers of hydrogen flowing into the Milky Way, providing a fresh influx of pristine, low metallicity gas that has not yet been processed through generations of stars. The motion of these clouds allows astronomers to trace the history of these gravitational interactions, using their velocity as a clue to map the past and future orbits of the satellite galaxies themselves. Studying these high-velocity clouds is crucial because they represent the galaxy's breathing apparatus, its method of inhaling new material and exhaling processed waste. They are the key to understanding how galaxies like our own grow over time by accreting fresh gas from the intergalactic medium, and how they self-regulate their own star-forming activity through energetic feedback. Their silent, high-speed journey through the galactic halo is a permanent reminder that even a seemingly stable spiral galaxy is a dynamic, evolving, and sometimes violent ecosystem. But our journey through the universe's fastest phenomena would be incomplete without venturing into the most speculative realm of physics, a place where the established rules are not just broken but entirely rewritten. This brings us to a purely theoretical concept that lives on the other side of the cosmic speed limit, the tachyon. Imagine a particle that is born traveling faster than light and can never slow down to cross that barrier. Unlike everything else we've discussed, which approaches light speed from below, a tachyon would exist in a state of perpetual superluminal motion, its very existence challenging the foundations of causality and our understanding of time itself. The concept arises from a quirky reinterpretation of Einstein's famous equation. In special relativity, any object with mass requires infinite energy to reach the speed of light. But the mathematics also allows for a solution where a particle has an imaginary mass, a complex number involving the square root of -1. This isn't a physical mass you could put on a scale, but a mathematical curiosity that implies a particle for which the speed of light is not a ceiling but a floor. Such a particle, a tachyon, would always be faster than light. If you tried to slow it down by adding energy, it would actually speed up, approaching infinite speed as its energy approaches zero. Conversely, to push it toward the light speed barrier from above would require an infinite amount of energy, effectively making the barrier just as impenetrable from the faster than light side as it is from our own. The most mind-bending implications of tachyons aren't about speed, but about cause and effect. According to relativity, if information could travel faster than light, it could theoretically arrive at its destination before it left its source, violating causality. Imagine you could send a tachyon message back in time to tell your past self not to send the message. This creates a paradox, a logical inconsistency that physicists find deeply troubling. If tachyons could be used to transmit information, they would open the door to these kinds of universe-breaking causal loops, where the effect precedes the cause, making the concept of a fixed timeline utterly meaningless. This is the primary reason most physicists remain deeply skeptical about the existence of tachyons as real, detectable particles. No experiment has ever found convincing evidence for them, and their theoretical framework is fraught with problems, including the potential for runaway reactions that would violate the conservation of energy. Yet, the idea persists in the imagination of scientists and science fiction writers alike because it represents the ultimate exploration of what might be possible beyond the boundaries of our current knowledge. They serve as a fascinating thought experiment, a tool for probing the absolute limits of our theories and asking the profound question of whether the speed of light is a true constant of nature or merely a horizon beyond which a completely different set of physical laws awaits discovery. While the fury of a quasar is driven by a single, monstrous black hole, there is another type of galactic engine that achieves similarly breathtaking speeds through the combined power of countless individual stars. These are starburst galaxies, cosmic cauldrons where star formation has been whipped into an absolute frenzy, and the collective energy of this stellar birth is so immense it can blow the galaxy's own potential future right out into the void. These are not gentle breezes, they are galactic-scale hurricanes, powerful outflows where superheated gas is ejected at thousands of kilometers per second. A relentless wind that can dictate the ultimate fate of an entire galaxy. The stage for this drama is set when a galaxy experiences a tremendous influx of gas, often triggered by a collision or a close encounter with a neighboring galaxy. This massive injection of fuel throws the system into chaos, igniting a firestorm of star formation that can be hundreds or even thousands of times more intense than what we see in our own placid Milky Way. In these dense, tumultuous regions, stars aren't born in isolation. They form in massive, crowded clusters, and they do so on a drastically shortened timescale. This means an enormous population of massive, short-lived stars is created all at once. These stars live fast and die young, and it is their spectacular deaths that power the incredible winds. Each supernova explosion acts like a piston in a vast cosmic engine, and with thousands of them detonating in quick succession, their collective shockwaves combine to drive a superwind, a coherent, galaxy-wide outflow that punches its way out of the galactic disk. The resulting wind is a complex and violent structure, a vast river of million-degree gas that is chemically enriched with heavy elements freshly forged in the hearts of those massive stars and their explosive deaths. This isn't just hydrogen and helium, it's a soup of oxygen, carbon, iron, and silicon, the very building blocks of planets and life. As this wind accelerates to speeds of 2,000 to 3,000 kilometers per second, it does more than just move fast, it fundamentally alters the ecosystem of its home galaxy. The wind violently sweeps up and entrains colder, denser clouds of gas from the interstellar medium, dragging them along in its flow and effectively robbing the galaxy of the raw material needed to form the next generation of stars. This process, a form of self-regulating feedback, ensures that the starburst cannot last forever. The galaxy is essentially shutting down its own star-forming factory by ejecting the fuel supply with tremendous force. The impact of these winds extends far beyond their home galaxy's borders. They act as a primary distribution system for heavy elements throughout the universe, injecting this enriched material into the relatively pristine intergalactic medium. This process, often called galactic pollution, is crucial for the chemical evolution of the cosmos. The gas that is ejected into these vast regions between galaxies will eventually cool and become part of the reservoir from which future generations of galaxies and stars will form, meaning that the products of one galaxy's furious life cycle become the seeds for another's. We can often see the spectacular effects of these winds in observations. The iconic starburst galaxy Messier 82 displays a brilliant halo of glowing filaments stretching tens of thousands of light-years above and below its disk, a direct snapshot of this material being violently expelled, a permanent testament to the incredible power of collective stellar energy to shape the cosmos on the grandest scales. But even as we consider the vast journeys of entire galaxies and the frantic winds from stellar nurseries, there's a far more subtle and profound way to measure our own motion through the cosmos, one that uses the oldest light in existence as a fixed reference point. This brings us to an incredible fact. By studying the faint afterglow of the Big Bang itself, we can calculate our absolute velocity through the universe. This isn't our speed relative to the Sun or the galactic center, but our true motion through the fabric of space-time, and it clocks in at a staggering 370 kilometers per second. This discovery was made by detecting a tiny but crucial distortion in the cosmic microwave background radiation, known as the dipole anisotropy. The cosmic microwave background, or CMB, is the cooled remnant of the first light that could travel freely through the universe, released about 380,000 years after the Big Bang. It fills all of space with an almost perfectly uniform glow, a microwave whisper that has been traveling for over 13 billion years to reach us. This radiation is the closest thing we have to a universal rest frame, a fixed background against which absolute motion can be measured. And when we point our most sensitive telescopes, like the Planck satellite, at this ancient light, we find it is not perfectly uniform. It appears very slightly warmer and bluer in one direction of the sky and cooler and redder in the exact opposite direction. This effect is called a dipole anisotropy, and it's the result of the Doppler effect applied to the oldest light we can see. Just as the pitch of a siren rises as an ambulance moves toward you and falls as it moves away, light waves are compressed or stretched by motion. The region of the CMB we are flying toward appears warmer because its light is blue-shifted, squeezed into shorter, more energetic wavelengths. The region we are flying away from appears cooler because its light is redshifted, stretched into longer, less energetic wavelengths. By meticulously measuring the temperature difference between these two poles, a variation of only about 0.003 of a degree cosmologists can calculate our precise speed relative to this primordial rest frame. The result is a velocity of 370 kilometers per second, or roughly 828,000 miles per hour, in the direction of the constellation Leo. This motion is a vector sum, the combined result of every gravitational pull and rotational dance we are part of. It includes our orbit around the Sun's journey around the galactic center, the Milky Way's own motion within the local group of galaxies, and the entire local group's fall toward the great attractor. The CMB dipole cuts through all of that complexity to give us our net velocity through the universe. It's a humbling reminder that there is no such thing as a truly stationary point. We are all in constant, high-speed motion, and the cosmic microwave background provides the ultimate stationary backdrop against which we can finally measure our own grand, silent voyage through the cosmos. But for all their staggering power, the relativistic jets from active galactic nuclei have a crucial limitation. Their immense distance makes them incredibly difficult to study in fine detail. Fortunately, the universe has provided us with a scaled-down, nearby version of these phenomena that acts as a perfect laboratory, right here in our own galactic backyard. These are microquasars, binary star systems where a stellar mass black hole or a neutron star is actively feeding on a companion star, and in the process launching its own pair of perfectly formed near-light-speed jets. It's a case of cosmic mimicry on a stellar scale, where the physics of the most powerful engines in the universe is replicated in a system small enough to fit within our own galaxy. The name itself is a perfect description, a micro version of a quasar. Instead of a supermassive black hole millions of times the Sun's mass, the engine is a compact object with just a few solar masses. Instead of consuming entire clouds of intergalactic gas, it's pulling a stream of material directly from the surface of a single, unfortunate companion star. Yet, despite this difference in scale, the underlying physics is remarkably similar. As material from the donor star spirals down into an accretion disk around the black hole or neutron star, it becomes superheated and generates intense magnetic fields. This creates the same conditions needed to funnel and accelerate some of that infalling matter into two narrow, oppositely directed jets that scream into space at relativistic velocities. The incredible advantage of microquasars is their proximity and their rapid change. While an active galactic nucleus might evolve over millions of years, a microquasar can go through entire cycles of outburst and quiescence in a matter of weeks or months. This allows astronomers to observe the entire life cycle of jet formation, from the initial triggering event to its eventual fading, in real time. We can watch how changes in the accretion rate directly influence the jet's power and velocity, providing a direct causal link that is much harder to establish in their gigantic cousins. It's like being able to study the principles of a hurricane by observing a powerful but contained whirlpool in a lab, rather than trying to measure the entire storm from within it. The champion and most famous example of this phenomenon is a system known as SS433, located about 18,000 light-years away in the constellation Aquila. This system is a true cosmic oddity and a gift to astrophysicists. It consists of a black hole or a neutron star locked in a tight orbit with a more massive companion star. The compact object is strip mining its partner, pulling material into a vibrant accretion disk. But what makes SS433 utterly unique are its jets, which are not only present but precessing. They wobble like a spinning top over a period of about 162 days. This wobble creates a spectacular helical pattern in the jets as they extend outward, a swirling corkscrew of matter traveling at a breathtaking 26% of the speed of light. We can actually see the Doppler shift in the light from these jets, providing direct observational proof of their incredible velocity. The side of the jet rotating toward us appears brighter and blue-shifted, while the side swinging away is dimmer and red-shifted. By carefully measuring this shift, astronomers can calculate the speed with astonishing precision. Furthermore, the jets in SS433 are not just made of electrons and protons. They are surprisingly rich in heavier atoms like iron, meaning the system is actively ejecting the building blocks of planets into the interstellar medium. This nearby microquasar is more than just a miniature replica. It's a detailed blueprint showing us the inner workings of universal engines that power the most luminous objects in existence, all from a front-row seat within our own galaxy. But to forge a true magnetar, the universe requires a perfect storm of conditions during a star's catastrophic collapse. A set of circumstances that channel the star's death throws into creating the most powerful magnets in existence. This process begins not with a gentle spinning up, but with a cataclysm of unbelievable violence, the core collapse supernova of a massive star. In these final moments, as the iron core implodes under its own weight, the conservation of angular momentum takes over. Just as an ice skater pulls their arms in to spin faster, the collapsing core, which may have been rotating slowly over its lifetime, begins to whirl at an ever-increasing rate. For a star destined to become a magnetar, this spin is accelerated to an extreme, with the newborn neutron star's surface completing a full rotation in just a few milliseconds. This isn't just fast, it is the astrophysical equivalent of a blender motor running at its absolute limit. This furious rotation is the primary ingredient for the runaway dynamo effect. The newborn neutron star is a seething ball of incredibly dense, electrically conductive fluid, a mixture of neutrons, protons, and electrons. As this fluid churns and convects due to the immense heat of formation, its motion, combined with the star's rapid spin, acts like a colossal electrical generator. Moving a conductor through a magnetic field generates an electric current, and here the entire star is the conductor, and its own internal, tangled magnetic fields provide the initial seed. The rotation twists and shears these internal fields, amplifying them exponentially in a runaway feedback loop. In a matter of seconds, the magnetic field can be boosted from an already impressive level to one that is 1,000 times stronger, creating the magnetar's signature ultra-powerful field. Yet, the story of a magnetar's speed is written by a separate, parallel event in the same supernova. The explosion that creates the neutron star is rarely perfectly symmetrical. Instabilities in the collapsing core can cause the supernova shockwave to be ejected more powerfully in one direction than another. This asymmetry acts like a rocket engine, imparting a tremendous kick to the newborn neutron star. This recoil can launch the magnetar across space at hundreds of kilometers per second, a velocity so high it can quickly escape the gaseous remains of its own stellar nursery. This means the very explosion that forges this incredible magnetic monster in its heart also has the power to throw it clear of its birthplace, sending it on a high-speed journey through the galaxy as a lone, hyper-magnetized wanderer. This dual origin, the spin-powered dynamo and the explosive kick, creates an object of terrifying power and motion. A magnetar is not a serene cosmic lighthouse, it is a seismic prison under unimaginable strain. Its crust of iron nuclei is locked into a crystalline lattice by the intense magnetic field, a field so powerful that it constantly stresses and fractures this solid surface. These starquakes release catastrophic amounts of energy, shaking the very fabric of the star and causing brilliant, random flashes of X-rays and gamma rays. It is a profoundly unstable existence, a testament to the fact that the most magnetically powerful objects in the universe are also some of the most violently chaotic, born from a perfect and fleeting confluence of spin, collapse, and explosive asymmetry. Yet for all the motion we've measured relative to the cosmic microwave background, this incredible velocity isn't our final destination. It's part of a much larger, more mysterious journey. Our entire local group of galaxies, including the Milky Way and Andromeda, is not merely drifting, it is being pulled, compelled by gravity on the very largest scales toward a specific, hidden point in the cosmos. This is the Great Attractor, an enigmatic region of space in the constellation Centaurus that exerts a gravitational influence so profound it is drawing us inward at roughly 600 kilometers per second. This isn't a gentle tug, it's a cosmic current, a relentless flow of thousands of galaxies all moving in concert toward a single, massive overdensity in the universe. The story of its discovery is a classic tale of cosmic cartography. For decades, astronomers have meticulously mapped the velocities of galaxies relative to the uniform backdrop of the cosmic microwave background. While the overall expansion of the universe causes galaxies to recede from us, their individual motions reveal a different story when you subtract that expansion. They show peculiar velocities deviations from the smooth Hubble flow, and when these were plotted, a startling pattern emerged. Galaxies across a vast volume of space, including our own, weren't moving randomly. They showed a coherent bulk flow, all sharing a common motion toward the same patch of the southern sky, a direction centered near the constellations Centaurus and Hydra. This implied the existence of a concentration of mass so immense, so gravitationally powerful, that it was dictating the motion of entire galaxies from hundreds of millions of light years away. They named this unseen gravitational master the Great Attractor, but identifying the source of this pull proved incredibly difficult for one simple reason. Its location lies directly behind the disk of our own Milky Way, in a zone of the sky astronomers call the zone of avoidance. This is the crowded, dusty plain of our galaxy, where light from distant objects is completely obscured by the myriad stars, gas, and dust of our own spiral arms. It was like trying to find a distant mountain range while staring directly into the glare of a brilliant, nearby city. For years, the Great Attractor remained a ghost, a gravitational signature without a visible source, its true nature hidden behind a cosmic curtain. The breakthrough came with the advent of telescopes that could see beyond visible light. Instruments like the Parkes Radio Telescope in Australia and various infrared space observatories could peer through the galactic veil. Radio waves and infrared light pass through the dust that blocks optical light, allowing us to map the universe hidden behind our own galaxy. What they found was not a single, monstrous object, but something far more grand and structurally significant, the Laniakea supercluster. This is our home supercluster, a vast filamentary network of over 100,000 galaxies, spanning 500 million light-years, all bound together by gravity. The Great Attractor is not a point, but a gravitational center of mass for this entire immense structure, a broad region where the density of galaxies, galaxy clusters, and most intriguingly, dark matter reaches a powerful peak. This changes our perspective entirely. Our motion toward the Great Attractor is not a journey toward a single cosmic monster, but our natural orbit within the Laniakea supercluster. We are like a planet orbiting the Sun, but on a galactic scale. The Milky Way, along with the entire local group, is falling toward the gravitational center of our supercluster. This center is dominated by a massive cluster of galaxies known as the Norma cluster, which acts as the core anchor point for the entire Laniakea structure. The pull we feel is the combined gravity of all the mass in this region. Not just the visible galaxies, but the immense, invisible halo of dark matter that forms the true gravitational scaffolding of the universe. This revelation ties the Great Attractor directly to the large-scale structure of the cosmos, the cosmic web itself. It is a node where filaments of dark matter and galaxies intersect, a grand central station in the network of the universe. Understanding this flow gives us a powerful tool for cosmography, mapping the universe's structure by tracing the motion of galaxies. By following the paths of thousands of galaxies, we can trace the gravitational topography of the cosmos, revealing where mass is concentrated and how it is distributed. This has led to the discovery of even larger gravitational influences beyond Laniakea. Our entire supercluster, including the Great Attractor, is itself being pulled toward an even more massive structure, hundreds of millions of light-years away, known as the Shapley supercluster, the largest known concentration of mass in our observable universe. Our journey is a nested one. We orbit within our local group, which falls toward the Great Attractor, which is part of Laniakea, which is itself being drawn toward Shapley. It is a profound reminder that gravity knows no boundaries, weaving the entire observable universe into a single, interconnected web of motion, with our galaxy playing a small but moving part in this grand cosmic dance. But even as we map these grand flows of galaxies, we are continuously reminded of the smaller, yet equally baffling, messengers that arrive from the depths of space, carrying energies that seem to defy the very laws that govern the cosmos. This brings us back to the enigmatic cosmic rays, but not the ones we discussed before. We now focus on the ultimate aristocrats of this invisible rain, the ultra-high-energy cosmic rays. These are the oh my god particles and their kin, individual subatomic projectiles carrying so much kinetic energy that their very existence presents a profound cosmological puzzle, one so sharp it has a name, the GZK paradox. To understand the depth of this mystery, we must first appreciate the invisible barrier these particles are up against. In the 1960s, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently calculated that the universe should not be a transparent highway for such immensely energetic protons. Their reasoning was brilliant and based on a simple collision course. The cosmos is not empty. It is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. This sea of low-energy photons is everywhere, a relic from the early universe with a present-day temperature of just about 2.7 degrees above absolute zero. For a proton traveling at 99.9999999% of the speed of light, however, these gentle microwave photons are no longer benign. Due to the extreme relativistic effects of its motion, the proton's perspective completely transforms the universe. That faint background radiation is dramatically blue-shifted, appearing to the proton as a furious storm of high-energy gamma-ray photons. This sets the stage for a catastrophic interaction. When such an ultra-relativistic proton collides head-on with one of these blue-shifted CMB photons, the meeting is anything than peaceful. The collision has more than enough energy to produce new particles, specifically a pion, a particle made from a quark and an antiquark. This process, known as the photomeson production, acts like a relentless friction for the speeding proton. Every time it slams into a CMB photon, it loses a significant chunk of its energy, producing pions and slowing down. Greisen, Zatsepin, and Kuzmin calculated that this interaction should impose a strict distance limit on how far these ultra-high-energy cosmic rays can travel. A proton with an energy above about 6 times 10 to the 19th electron volts should be able to journey no more than 150 to 200 million light-years before the cumulative effect of these collisions drains its energy down below that threshold. This theoretical limit became known as the GZK cutoff. It implies that any cosmic ray we detect with energy beyond this limit must have originated from within our local cosmic neighborhood, a relatively small bubble in the vast universe. And yet, our detectors tell a different story. Observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have repeatedly recorded these ultra-high-energy events, particles that clearly possess energies far beyond the GZK limit. This is the heart of the paradox. We are seeing particles that, according to our best understanding of physics, should not be able to reach us. Their existence forces us to confront two equally thrilling possibilities. Either these cosmic rays are coming from incredibly powerful sources much closer to us than the GZK distance allows, which itself is a puzzle because we don't know of any such capable engines in our immediate vicinity, or our understanding of physics at these extreme energies is incomplete and needs revision. The hunt for nearby sources has been frustrating. Tracing the paths of these charged particles is nearly impossible because their trajectories are scrambled by the Milky Way's magnetic fields long before they reach us. We can point to active galactic nuclei or powerful gamma-ray bursts as potential accelerators, but the nearest known candidates of such phenomena are still often far beyond the GZK horizon. This has led physicists to consider more exotic explanations. Perhaps there is a flaw in our models of particle interactions at energies far beyond what we can create in human-built colliders like the Large Hadron Collider. Maybe entirely new, unknown physics is at play, such as violations of Lorentz invariance, a cornerstone of Einstein's special relativity, which could subtly alter the energy threshold for the GZK process. Or perhaps these particles are not protons at all, but heavier atomic nuclei like iron, which interact with the CMB in a slightly different way and might have a different energy loss profile. Each potential solution opens a new door to a deeper understanding of the universe, making the detection of every single one of these rare, ultra-high-energy particles a monumental event in astrophysics, a direct challenge from the cosmos to our current models, and an invitation to explore the frontiers of what we think is possible. But for all the immense power generated by a supernova, there is another, even more exotic and precise cosmic collision that forges the very heaviest elements in the universe and flings them into the void at a staggering fraction of light speed. This is the kilonova, the spectacular and fleeting aftermath of two neutron stars merging. When these incredibly dense stellar corpses spiral together in a final, fatal dance, they do more than just create gravitational waves and a gamma-ray burst. They become the universe's ultimate heavy element factory, ejecting a spray of newly forged gold, platinum, and uranium at speeds that can reach 30% the speed of light. The journey to this cosmic forge begins with a binary system that has already survived the violent deaths of two massive stars. Two neutron stars, each containing more mass than our Sun crushed into a sphere the size of a city, are locked in a decaying orbit. For millions of years, they emit gravitational waves, those subtle ripples in space-time, slowly but relentlessly losing orbital energy. This causes them to spiral closer and closer together, their orbits tightening until in the final milliseconds, they are whipping around each other thousands of times per second at a significant fraction of light speed. The final merger is an event of almost unimaginable violence. The two ultra-dense bodies don't just gently touch, they rip each other apart with immense tidal forces, shredding their own structures and creating a maelstrom of neutron-rich matter. It is in this hot, chaotic debris field that the magic of nucleosynthesis occurs under the most extreme conditions. The intense density and temperature, combined with a flood of neutrons, allow for a rapid capture process known as the R process. Atomic nuclei are bombarded by free neutrons so quickly that they don't have time to radioactively decay between captures. This allows them to grow exponentially in mass, climbing up the periodic table in a matter of seconds to form the most stable heavy elements. This isn't the slow fusion process of a star's life. It's a violent, explosive assembly line that can only occur in such an energy-rich environment. The result is a cloud of radioactive debris enriched with rare elements like gold, platinum, iodine, and even uranium, the very elements that are scarce on Earth but essential for modern technology and even for life itself. This newly created treasure trove of heavy elements isn't just sitting still. It is expanding outward with ferocious speed, driven by the incredible energy released in the merger. The ejector is launched in two primary ways: a slower, denser tidal tail pulled out by gravitational forces during the final moments before collision, and a faster, more spherical wind driven by neutrinos and the decay of the hypermassive neutron star or short-lived black hole that forms at the center. It is this second component that can achieve the most breathtaking velocities, accelerating to nearly 100,000 kilometers per second. To grasp that speed, imagine a blob of material massive enough to form several of our moon, traveling from the Earth to the moon in less than 4 seconds. The observable signature of this high-speed radioactive expansion is the kilonova itself, a transient astronomical event that shines not primarily from heat, but from the radioactive decay of all those freshly minted heavy elements. The ejected cloud is initially incredibly opaque, as the heavy atoms have complex electron structures that block light. But as the cloud expands and thins at its incredible velocity, it becomes transparent over a period of days, causing the light curve to rise and then fade. The light itself has a distinctive blush, often described as a red to blue transition, which comes from the different opacities of the various lanthanide elements within the ejector. The first confirmed kilonova was observed in August 2017, accompanying the gravitational wave signal GW170817 and the short gamma-ray burst GRB170817A. The spectroscopic analysis of that event provided the long-sought smoking gun, evidence that neutron star mergers are indeed a primary cosmic source for the R process elements, finally solving a decades-old mystery about the origin of the heaviest elements in the universe. This incredible process forever links the grandeur of cosmic speed to our own existence. The gold in a wedding ring, the platinum in a catalytic converter, and the uranium used for nuclear power were all once part of a spectacular, high-speed spray ejected from the collision of two dead stars billions of years ago. That material traveled across the galaxy, eventually mixing with the nebular cloud that would form our solar system. We are literally walking stardust, but for these rarest of elements, our origins are even more spectacular. We are the children of a kilonova, our technology and our very biology built from atoms that were forged in a split-second cataclysm and then flung across the cosmos at nearly a third the speed of light. A permanent testament to the fact that the universe's most violent and fastest events are directly responsible for the richness of our world. Yet while the kilonova flings its precious cargo into the void, there exists another class of stellar remnant that has perfected a different kind of motion, achieving a rotational velocity so extreme it defies our very understanding of solid matter. These are the millisecond pulsars, the universe's ultimate spin masters, and they hold the record for the fastest stable rotation of any known object in the cosmos. To witness one is to watch a city-sized ball of ultra-dense nuclear matter completing hundreds of full rotations every single second, with its equator moving at a significant fraction of the speed of light. This isn't a chaotic, explosive spin like that of a newly born magnetar. It is a precise, metronomic, and incredibly stable rotation that rivals the best atomic clocks here on Earth. The story of how a millisecond pulsar attains such breathtaking velocity is a cosmic tale of resurrection and rebirth. It begins with a typical pulsar, the dense neutron star remnant of a supernova, spinning perhaps a few dozen times per second, already incredibly fast by any earthly standard. But this object is not alone. It exists in a binary system with a companion star. Over millions of years, as the two stars orbit each other, the intense gravity of the neutron star begins to pull material away from its partner. This stream of gas doesn't just fall directly onto the surface. It forms a swirling accretion disk around the pulsar, much like water circling a drain. And as this material spirals inward, it carries with it a tremendous amount of angular momentum, the property of an object that defines its rotational motion. This process of accretion acts like a cosmic crank, gradually winding the pulsar up to faster and faster speeds. Think of it as pushing a merry-go-round. With each gentle, consistent push, you add a bit more spin. Over hundreds of millions of years, this constant feeding of matter and angular momentum from the companion star can accelerate the pulsar's rotation from a modest few dozen times per second to an astonishing several hundred times per second. The energy transfer is so efficient that it can transform an old, slowly spinning pulsar into a youthful-looking speed demon, effectively recycling the dead star and giving it a new, hyperactive lease on life. The companion star, having donated much of its mass, is often left as a depleted white dwarf, a ghost of its former self. The physics happening at the surface of such a rapidly spinning object is almost beyond comprehension. A typical millisecond pulsar might have a radius of only about 10 kilometers, but it can complete a full rotation in just 1.4 milliseconds. This means a point on its equator is moving at approximately 20% the speed of light, or about 60,000 kilometers per second. At that velocity, the centrifugal forces are so immense that were it not for the crushing gravity of the neutron star, 100 billion times stronger than Earth's, the star would literally tear itself apart. The magnetic fields of these objects are also fascinating. While they are still incredibly powerful, they are often orders of magnitude weaker than those of their younger, slower pulsar cousins. This is likely because the process of accretion actually buries and dampens the original magnetic field, allowing the star to be spun up without the magnetic braking that would normally slow it down. We detect these incredible spinners through their lighthouse like beams of radio waves, which sweep across our line of sight with a regularity that is utterly precise. Their pulses are so steady that they can be used as celestial navigation beacons, and astronomers have proposed using networks of them to create a galactic positioning system. The existence of millisecond pulsars is a brilliant demonstration of the dynamic and interactive nature of our universe, where a dead star can be reawakened and accelerated to its physical limits through a graceful, billion-year-long gravitational dance with a companion. They stand as a testament to the fact that in the cosmos, speed isn't always about a single, violent explosion. Sometimes it's the patient, relentless result of a perpetual cosmic partnership. But if the explosive spray of a kilonova represents matter flung outward by a cataclysm, and the precise spin of a millisecond pulsar showcases rotational velocity, then our next phenomenon requires us to consider an entirely different kind of motion, one that is both everywhere and nowhere, felt only through its gravitational influence. This brings us to the enigmatic realm of dark matter, the invisible scaffolding of the cosmos. While it doesn't emit, absorb, or reflect light, making it completely transparent to our telescopes, this doesn't mean dark matter is stationary. In fact, it is constantly in motion, swirling around and through galaxies at breathtaking speeds that can reach hundreds of kilometers per second, its velocity dictated solely by the relentless pull of gravity. The story of dark matter's motion is written in the very rotation of galaxies themselves. When astronomers first measured how fast stars orbit the centers of spiral galaxies, they expected to see a familiar pattern. Stars closer to the center should orbit very quickly, while those farther out in the spiral arms should move more slowly, just as planets in our solar system orbit more slowly the farther they are from the Sun. But the observations revealed something astonishingly different. Stars at the outer edges of galaxies were orbiting just as fast as those near the center. This flat rotation curve implied there was far more mass in the galaxy than could be accounted for by the visible stars and gas, mass that was spread throughout a vast spherical halo extending far beyond the luminous disk. This invisible mass is dark matter, and its gravitational pull is what keeps those high-speed stars from flying off into intergalactic space. The velocity of a star on the outskirts of a galaxy, cruising along at 250 kilometers per second, is a direct measurement of the dark matter halo's gravitational grip. These dark matter particles are not simply tracing orderly circles like stars in a disk. Computer simulations of structure formation in the universe show that dark matter, because it doesn't interact with itself or other matter except through gravity, forms vast, roughly spherical halos around galaxies. Within these halos, the particles follow chaotic, elongated orbits, zooming in toward the center and then swinging far back out again. Their typical velocities are on the order of hundreds of kilometers per second, a frantic, high-speed dance that defines the gravitational potential well which the entire visible galaxy sits within. This motion is crucial for galaxy formation. In the early universe, tiny fluctuations in the density of dark matter provided the seeds for gravity to work on. Dark matter clumped together first, its gravitational pull acting as a cosmic attractor, drawing in ordinary gas that would eventually cool, condense, and form the stars and galaxies we see today. Without these fast-moving, invisible particles carving out the gravitational landscape first, the universe would look utterly different, far fewer galaxies, and nothing like the grand spiral structures we observe. The fact that dark matter moves at such high speeds is also the greatest challenge to detecting it directly here on Earth. Our entire planet is sailing through this galactic halo of invisible particles. Think of it as driving through a ghostly rainstorm where the raindrops are dark matter particles, and we are moving through this storm at the same 230 kilometers per second that our solar system orbits the galactic center. Scientists have built exquisitely sensitive detectors deep underground, shielded from cosmic rays, in the hope that a dark matter particle will, on very rare occasions, bump into the nucleus of an atom in the detector and impart a tiny amount of energy, a minuscule vibration. But that faint signal depends on the speed of the particle. If the dark matter is moving too slowly relative to the detector, the collision might not have enough energy to be recorded. If it's moving at just the right speed and from the right direction, the chance of a detectable interaction increases. This is why some experiments report potential seasonal variations. As Earth orbits the Sun, the direction of our travel through the galactic dark matter halo changes, slightly modulating the expected average velocity of the particles we might encounter. We are essentially using our own planet's motion as a tool to hunt for the faintest whisper of an impact from the universe's most abundant, yet most elusive high-speed material. And finally, we arrive at the ultimate expression of cosmic speed, a concept that defines the very boundary of reality itself and brings our journey full circle. While we have marveled at objects moving through space at near light speeds, the single fastest phenomenon isn't an object moving at all. It is space itself, expanding and stretching in a way that carries entire galaxies away from us at velocities that utterly dwarf anything else we've discussed. This is the Hubble flow, the relentless expansion of the universe, and it means that for galaxies beyond a certain point, the very fabric of space-time between us is growing so quickly that they are receding faster than the speed of light. This isn't a violation of Einstein's rule. Nothing is moving through space faster than light. Instead, the space between us is multiplying, creating more distance at a rate that light itself can never overcome. This creates a fundamental and permanent limit to our observable universe, a boundary known as the cosmological horizon. Imagine you are on a moving walkway that is steadily accelerating. Someone standing a short distance away can still walk toward you and reach you even as the walkway expands, but another person standing much farther down the accelerating walkway would find that no matter how fast they walk toward you, the walkway itself is stretching apart faster than their maximum speed. They are forever beyond your reach. This is the fate of countless galaxies. Their light, emitted billions of years ago, is still traveling toward us through the expanding space, and we can see them as they were in the distant past. But any light they emit today is destined to wander an ever-increasing void, the space between us growing so rapidly that the photons will never make any forward progress in the vast gap. They have effectively vanished from our future, crossing an invisible horizon beyond which no signal, no message, and no future information can ever pass. This ultimate speed limit isn't just a curiosity. It is the definitive factor that shapes the entire scope of human knowledge and exploration. It means the universe has a built-in expiration date for discovery. As the expansion continues to accelerate, driven by the mysterious force of dark energy, more and more galaxies will slip across this horizon and disappear from our view. The observable universe, the portion we can potentially know, is actually shrinking in terms of the number of galaxies within it, even as the whole universe continues to grow. We are living in a privileged moment in cosmic history, a time when the afterglow of the Big Bang is still visible and a vast array of galaxies are within our cosmological sight. Billions of years from now, astronomers in our Milky Way will look out into a much emptier cosmos, their telescopes revealing only the few nearby galaxies bound to us by gravity, with all other island universes having faded into an impenetrable darkness, their stories and light lost to the void forever. This profound fact serves as the ultimate bookend to our exploration of the universe's fastest objects. From the subatomic spin of a neutron star to the galactic winds of a quasar, and now to the horizon of reality itself, speed is the fundamental currency of the cosmos. It dictates what we can see, what we can know, and ultimately our place in the grand narrative of the universe. These 30 facts are not just a list of records. They are a testament to a universe that is dynamic, violent, beautiful, and always in motion, inviting us to look up with wonder at the incredible velocities that shape everything from the atoms in our bodies to the fate of the entire cosmos. From the unfathomable constancy of light's speed to the patient billion-year acceleration of our Voyager probes, The universe is a symphony of motion played at every conceivable tempo. We've witnessed stars catapulted from galactic centers, particles carrying the energy of a pitched baseball, and the very fabric of reality stretching at an ever-increasing rate, carrying galaxies beyond our sight. This breathtaking range of velocities is more than just a cosmic record book. It is the key to unlocking the deepest secrets of physics. Each of these high-speed phenomena acts as a natural laboratory, testing the laws of relativity, quantum mechanics, and cosmology under conditions we could never hope to recreate on Earth. The spin of a millisecond pulsar probes the very limits of material strength. The detection of an ultra-high-energy cosmic ray challenges our understanding of particle acceleration, and the accelerating expansion of space itself points toward a mysterious dark energy that dominates the cosmos. By studying these cosmic speed demons, we are not merely cataloging distant curiosities. We are engaging in a fundamental exploration of what is possible. They force us to question, to innovate, and to sometimes completely rewrite our understanding of reality. Every new discovery, from a hypervelocity star to a gravitational wave chirp, is a testament to human curiosity and our relentless drive to comprehend the universe we inhabit. This journey to the edges of physics reminds us that the cosmos is far stranger, more dynamic, and more magnificent than we often dare to imagine. So, which of these incredible speedsters left you the most awestruck? Was it the lonely journey of a rogue planet or the focused power of a quasar's wind? Let us know in the comments, and don't forget to like and subscribe for more journeys to the edges of